For those of you who don't know, the dual numbers are numbers of the form a plus b epsilon, where epsilon squared is equal to 0. There are a handful of ways to construct these numbers, but in my opinion, the most straightforward is to define the dual number version of 1 to be the 2 by 2 identity matrix, and epsilon to be this matrix. The dual numbers are then just linear combinations of 1 and epsilon. Note that 1 and epsilon are linearly independent. This is important since we need the dual numbers to have a unique representation as a linear combination of 1 and epsilon. Our goal is going to be to use the dual numbers to take derivatives of multivariable functions. To do this, we are going to need vectors with dual number entries. The term vector is being used loosely here, since the dual numbers are not a field. Epsilon is not invertible. However, that's okay. All we need is for scalar multiplication and vector addition to be possible, and for each quote-unquote vector to be uniquely represented by a vector plus another vector times epsilon, which they are, since each entry of the vector has a unique representation in that form. Finally, we need a way to extend multivariable functions from Rn to Rm to these dual number vectors. Fortunately, this is straightforward for any such function whose scalar entries can be represented as a rational function or a potentially infinite polynomial, perhaps in several variables, by simply plugging in. With all of this groundwork done, what I hope to convince you of is that differentiation in multiple variables is the exact same thing as differentiation in one variable. We can now define the derivative phi prime of a of a multivariable function phi at a point a that can be extended to the dual numbers, if it exists, as a matrix satisfying this equation. The differential d phi at a is then just the linear map represented by phi prime of a. In the last section, we already did the work that guarantees that this matrix will be unique, as phi prime of a times h will just be some vector in Rm. So, how does this actually work out computationally? Let's try a few examples. In each, we will use dx, dy, and dz to denote the coordinates of h. These are just going to be mundane real numbers. First, because I'm required to by law, let's consider the example of phi of x equals x squared, just to see how things work out in the single variable case. In this case, h is just the scalar dx. You've probably seen this example a billion times, so here it is all at once. Notice that once all is said and done, since 2x dx is a linear function of dx, d phi in this case is 2x dx, and 2x is its 1 by 1 matrix, the derivative, which in this case is the same thing as d phi divided by dx, since dx is just a mundane real number. Anyways, let's consider the less trivial example of a function from R3 to R2 defined as shown. If a is some particular input vector, and h now has entries dx, dy, and dz, then we can plug in a plus h epsilon as before, and after some algebra, we get this. We can pull out epsilon, and notice that we can pull out h out of this vector to end up with a matrix times the vector. By our definition, phi prime of a is this matrix, and d phi is this linear map. Note that this matrix has as many rows as the range has dimensions, and as many columns as the domain has dimensions. In the special case where the range has only one dimension, we can say that the partial derivatives of phi are just the entries of this matrix. And this matrix does have a geometrical significance, which you can learn about in detail in this video that has more views than this one ever will. And yes, this can all be done with limits, but limits are overrated, and I wanted to keep the video short. Now, if you'll allow me to complain, you know what I don't get? Why there's so much terminology for all the special cases. Often, this matrix is actually called the Jacobian, except in the special case where phi is scalar valued, and the matrix is turned sideways, where it suddenly becomes the gradient. There is disagreement as to whether or not to call the linear map itself the differential, or the derivative, or the total differential, or the total derivative, and when you plug a specific vector into that linear map, but again only in the special case that I mentioned earlier, it's suddenly called the directional derivative. Now in my opinion, this is kinda stupid. I'm all for teaching the interpretations of special cases, but why clutter everything by changing the names from the one-dimensional case at all? Well anyways, that's all I wanted to talk about in this video. Expect me to make a more in-depth exploration of this approach on my website at some point. The link will be in the description if or when it is done. Bye.